Hi, everyone. All right, so today we're starting off with one of the most important topics in chemistry and biology, how atoms bond together. So every substance around you exists because atoms interact. The air you breathe, the water you drink, even the molecules inside your cells. On their own, atoms are usually unstable, except, of course, the noble gases that we talked about last week. So they tend to combine with other atoms to become more stable. These interactions form molecules and compounds, and those determine the physical and chemical properties of matter. And by the end of this lesson, you should understand why atoms form bonds, the different types of bonds, and how bonding explains real world properties like melting point, conductivity, and molecular shape. Okay, so valence electrons are electrons in the outermost energy level of an atom. So these electrons are the farthest from the nucleus and are held the least tightly, which makes them the ones that participate in chemical reactions. So atoms don't interact using their inner electrons; they interact using these outer electrons. And so the number of these valence electrons determines how reactive an element is and what kinds of bonds it can form. For example, atoms with full outer shells tend to gain, or with almost full outer shells tend to gain electrons, while atoms with only one or two outer shells tend to lose them. So in many ways, chemistry is really the study of how atoms try to manage their valence electrons. So the periodic table tells us how many valence electrons an atom has. When you move across the row from left to right, atoms gain one valence electron. And then when you move uh, throughout the column, when you move down a column, the atoms keep the same amount of valence electrons. That means elements in the same column behave similarly, such as lithium, sodium, potassium. They all react violently with water because they each have one valence electron they want to lose. So the periodic table isn't just a list of elements, it's a map of chemical behavior based on electron arrangement. So atoms tend to be the most stable when they have 8 electrons in their outer shell. This idea is called the octet rule. You can think of atoms as trying to achieve a full outer shell similar to noble gases, which are naturally stable and unreactive. To reach that stable configuration, atoms will gain electrons, lose electrons, or share electrons with other atoms. Almost every chemical bond you will study comes from the simple goal: atoms rearranging electrons so their outer shell becomes full. So bonding isn't random, it's driven by stability. So depending on how many valence electrons an atom starts with, it'll try to reach 8 in different ways. Atoms with 5, 6, or 7 valence electrons usually gain or share electrons because that gets them closer to 8. Atoms with 1, 2, or 3 valence electrons usually lose them instead, which leaves a full shell underneath. This is why metals tend to form positive ions and nonmetals tend to form negative ions. So simply knowing where an element is on the periodic table lets you predict how it will behave chemically. And so, what are ions? An ion is simply an atom that has a charge because it gained or lost electrons. If an atom loses an electrons, it ends up with more protons than electrons and becomes positively charged. If it gains electrons, it ends up with more electrons than protons and it becomes negatively charged. So it's important to think as electrons as negatively charged. So the more negative it is, the more electrons there is. Right. So if something is uh, negatively charged. So look at that, for example, this image. So this has 5 protons and 6 electrons. That means overall this has a -1 charge. And then this has 6 protons and 5 electrons. So protons are positively charged and electrons are negatively charged. And overall there's a +1 charge, right? Because protons are positive. And then here, the atom is neutral, right? Because there's 6 protons and 6 electrons, meaning the sixes cancel out, so that means 0, and that means the atom is neutral. Okay, and then so this is an example of uh, where one valence electron from sodium is being transferred to chlorine that has 7 valence electrons. So sodium can become stable by losing an electron. You can see here, sodium has 1 electron on its most outer shell, but on the second shell, sodium has 8. And so when sodium transfers its electron to chlorine, both atoms achieve full outer shells. So sodium becomes positively charged and chlorine becomes negatively charged. And how strongly they interact with each other um, is because of how these opposite charges pull together. And so remember, opposites attract. So sodium positively charged, chlorine negatively charged. And so this attraction between oppositely charged ions is called an ionic bond. And in an ionic bond, electrons are transferred from one atom to another instead of shared. We'll talk about what shared means later. And so the resulting positive and the negative ions stick together due to electrostatic attraction. And so, how do we balance ionic compounds? So, ionic compounds must always be electrically neutral overall. So, for sodium and chlorine, since sodium is +1 and chlorine is -1, it only takes one of each to balance each other. But here for calcium, there's a 2 plus positive, meaning there's 2 protons more than electrons. And to balance that out, we need 2 calciums, right? Two chlorines that are -1 charged. And on the other end, we have lithium here that's a positive, and then sulfur here that's -2, right? And then so that means we need 2 lithiums to align with the -2 of the sulfur. Okay. And in general, ionic compounds are hard, brittle crystals with very high melting points. And then when they're dissolved in water, they conduct electricity. So contrary to what you might have seen in movies and stuff, you actually need salts in water in order for them to conduct electricity, not just pure water. And then on the other end, we have covalent bonds. So instead of transferring electrons, the atoms share electrons instead. So this type of bond is called a covalent bond. Covalent bonds usually form between nonmetals where neither atom strongly wants to lose electrons. By sharing electrons, both atoms count the shared electrons toward filling their outer shells. So the bond is held together because each nucleus is attracted to the shared electrons, and most molecules in living organisms, including water, sugars, proteins, are held together by covalent bonds. And so this is a quick image showing the difference between covalent and ionic bonds. And ionic bonds, electrons move from one atom to the other. So that's to the right. And then in covalent bonds, the atoms are sharing their electrons with each other. And what about for covalent bonds? So how do we know how many bonds each atom can form, right? And so one of the probably the most common chemical compound that you know is water, right? Water has 2 hydrogens and 1 oxygen. That's why we call it H2O. And so oxygen needs 2 electrons to fill its outer shell, and hydrogen needs 1. So oxygen forms 2 covalent bonds, one with each hydrogen atom creating water. And so how do we know how many bonds? Right? So here on this summarized periodic table showing the valence electrons, we see oxygen with 6 valence electrons, right? And since oxygen is trying to reach 8 because of the octet rule, it wants to bind with 2 things, and then that's going to be 2 hydrogens, right? So the octet rule applies for the second and third rows. However, the octet rule doesn't apply for the first row, right? So for hydrogen and helium, their most outer shells only have 2 electrons, right? And then as you go on, so there's 2 electrons here, and then the next row becomes 8 electrons, and then the next row becomes another 8 electrons, right? And then electrons really try to fill up that first row first, first shell first, and then it'll fill up its second shell, right? And again, the maximum is 2 on the first shell, 8 on the next shell, and then 8 on the other shell. And then so oxygen is trying to fill up 2 more because it wants to reach 8. And then so atoms can share more than one pair of electrons. And so for H2O, we're only seeing one single bond with each hydrogen, right? And uh, so sharing one pair forms a single bond, sharing 2 pairs forms a double bond, and sharing 3 pairs forms a triple bond. And the number of these bonds depends on how many electrons an atom needs to become stable. So we already went over how hydrogen only needs 1 more to fill its outer shell, and oxygen needs 2 more to fill its outer shell. And then so if we look at carbon and nitrogen on, so here carbon is on the fourth column, right? And then so it's going to need 4 more in order to get to 8 valence electrons. And then we look at nitrogen here. It has 5, so it needs 3 more to get to 8 valence electrons. And that's really important, right? And then so all over nature, you're going to see carbon bonded to 4 things, and nitrogen bonded to 3 things, and oxygen bonded to two things. And so uh, there's different kinds of covalent bonds. Uh, there can be single bonds, right, as we talked about with water. There can be double bonds and then triple bonds. And again, all of these are atoms trying to achieve the octet, so 8 valence electrons, so 8 most outer electrons. So here we have water. So we have oxygen that originally has 6 valence electrons. So it's sharing one of its valence electrons with hydrogen and sharing another valence electron with hydrogen. And then those hydrogens in turn are sharing one of their electrons to oxygen. And then this hydrogen is sharing one of its electrons with oxygen as well. And so that makes all of them really happy, right? Because they all get to fill their most outer shell. And again, hydrogen only requires 2 uh, for its most outer shell to be happy. Carbon dioxide, on the other hand, so if you look over here, carbon dioxide has 2 double bonds. And then, so it's important to note that carbon here, as we stated earlier, likes to be bonded to 4 things. And so if you look at what electrons carbon is sharing, right, it's sharing. So here, the carbon electrons are the pink dots, right? So for carbon, the 2 inner shells are filled, and then the most outer shell has 1, 2, 3, 4, right? And then so different from this bond with oxygen and hydrogen, carbon is actually sharing 2 of its valence electrons to oxygen, and then oxygen in turn is sharing another 2, right? And similar to this one, oxygen is happy when it's bonded to 2 things, so that double bond right there makes the oxygen happy. It doesn't want to bond to any more things because, right, it started with 6, now it's 8. And then it's happening here on the other side as well, right? And then now, so the carbon is happy now because it has 2 electrons from one oxygen and then 2 electrons from another oxygen. Okay, and then overall, this this carbon has now has 8 total electrons that it's orbiting the nucleus. And then finally, we have triple bonds, right? We talked earlier about how nitrogen likes to be bonded to 3 things. And then so nitrogen bonding to itself 3 times, it's perfect, right? So this electron is being shared with the other nitrogen, and then these 3 are being shared with the other nitrogen as well. Okay, so as more electrons are shared, the bond becomes shorter and stronger. So triple bonds are actually stronger than double bonds, and double bonds are stronger than single bonds.